Okay, we're going to be starting chapter 5, which is all about the single cycle processor. The introduction to the data path of how a processor works. So this is the core part of the course. Everything that we were learning before this prepare us to understand the processor part. So we already talked about the CPU performance factors, function counts, and CPI in cycle time. And we already looked over how to make an ALU. We didn't in the ALU, but we some parts of it, and we know how to expand it, right? And in this chapter, we're going to cover just a simplified version of the MIPS data path and control, and the simplified version being a single cycle version. In the next chapter, we'll look at a more realistic pipeline version, but again, it's going to be simplified compared to what processors look like. And we're also only looking at a subset of the instruction. Because if we looked at all the instructions, the diagram would just be way too messy for the introduction class. For instruction execution, I already know that we're going to use the PC to get the instruction address, and we need the data path to fetch that instruction from it. Okay. Then we need to decode that instruction, figure out what register that we need to read from. And we also need to decode the instruction to decide what exactly are we supposed to do with these registers, right? Is it going to be some arithmetic results? Do we need to go to memory by calculating the address plus the offsets? Or are we trying to branch by changing PC? So if we are accessing memory, we need to know that we're accessing the memory. And then if we need to write back to the register, we also need to figure that out from the instruction, right? We always have to increment PC by something. Usually it's PC plus 4, but it could also just be changing PC to the target address. If we're So here is our execution cycle. Okay. First, obtaining the instruction from the program source. Okay. So instruction fetch. Then we're going to decode the instruction to determine the required actions, right? And then we're going to grab the operands that the instruction told us to grab from the register file, form our instruction, whether it's going to be add, subtract, or calculating the base address plus the immediate offset. That's what the execute stage is for. And if we needed to grab from memory, it would be after this execute stage. If we were writing to memory, it would also be after the execute stage. And for all of our instructions that need to write back to the register file, we also need to store those results. And we go and repeat the process. So we're going to be covering first the single cycle implementation. So we're going to build a data path and control that can execute one instruction per cycle. And it will only do one instruction per cycle. And every single instruction will take one cycle. So the benefits of this, it's simple and easy to understand. And the data path is going to come directly from the FSA. The drawbacks are that it's going to be a slow implementation. The clock cycle needs to accommodate the longest instruction. So even if your add instruction done at half the time of, say, your load word instruction, your add instruction will take the same amount of time as the load word instruction. Because the data path block needs to be able to accommodate the longest instruction. Can't have this dynamic clock based on the instruction. But as I mentioned before, we will cover a pipeline implementation in the next chapter. But for now, it's best to start with the simplest design for you guys to understand it first, right? So we'll see how we can speed this up. But this is a key concept of single cycle. Because if you don't understand why the clock cycle needs to accommodate the longest instruction, understanding the pipeline version is not going to be easy. So first thing is, what kind of blocks do we need? So what do we need to start with in order to make this data path?
Registers.
Yeah, we need registers. What else do we need?
ALU.
ALU. What else do we need?
Data memory.
Some way to access memory. Anything else?
The control.
Yeah, we do need control. So control is going to do things like decode the instruction for us, right? Need a program counter, right?
Mhm.
What about for branching? What do I use? What about for incrementing program counter? Am I going to be using that ALU or is that going to be used up?
The ALU.
The ALU is going to be used up. So we need some other adder in order to implement program counter. We should also have some other adder to calculate target address. So we need a lot of these different blocks, so we can just kind of figure that out by looking at the different instructions that we need to implement and start from there. And then the question that we should answer after we have, these are the blocks I'm going to start with based on what I think I need for now to implement these instructions. How do I connect them? What order should they be connected in? So which one should go first, and then what should come after that? What should be last? Things like that. So this is the first checkpoint. Let's see, what is your code? Your code for today is 801. So answering these questions will help us figure out this ordering of our data path. So which is true about the ALU and the register file in MIPS? Eight zero one. think most of us are done working on this. We're not quite at the threshold, so please talk to people around. You can discuss your answer.
And then it comes all the way back over here. Like it's all. I think. Yes. Typically, it must be a for. We look up this. Just thinking of the stems. Yes.
Do you resubmit your answer to your request?
Lead people straight.
So we have some good movements. Right. So let's just go through this one bullet point at a time. So the ALU always performs an operation before accessing the registers. Is this true or not?
So you still the whole instructions.
So what would the ALU be operating on? This is the first question we should ask ourselves.
The input from the memory and instructions.
So input from the instruction. The instruction tells you what about the inputs of the ALU?
What to do with it.
What to do with it? But what else does it tell you?
Where to put it. And
Yes, where to put it? What else does it tell you? There's one more key factor that has to do with accessing the registers.
Where it's operating on.
What it's operating on, right? So, and what it's operating on is
Released on the register.
from the register. So the ALU cannot perform an operation before accessing. We need to get the data from the registers first, right? So we can't always perform an operation before accessing the registers. So it's not A. We can sometimes perform an operation before accessing the registers because we don't have anything to operate on. So then it's C or D. So the register file is always accessed before the ALU. So we know that it is accessed before the ALU. The question is it always accessed before the ALU?
I would think so.
Right? We need the data from the register file in order to do any operation. So R type, I need those registers, RSRT, I type, I need RSRT. And then for the other type of jumps, I'm just not using the ALU or the register file. So it's not incorporated here, right? So for our subset, the register file is always accessed before the ALU. So in terms of our data path ordering, what does that tell us about the register file and the ALU?
The register file needs to come first.
The register file should come first. So then the next question that will help us about this ordering is which is true about the ALU and memory in MIPS. And more specifically, let's just think about data memory in this case. I didn't see answers change that much on the poll. Is anyone still thinking about this? Alright, so we are not at threshold again. But answers are changing towards the correct answer. But you should do the pure discussion. Talk about why you answered your answer. And then resubmit after the discussion.
That's the. Go for it first, so it's funny. I'm trying to. It's like, I thought I was saying something about the registering.
Hey, again, your discussion slowing down. Do resubmit your answer if you were convinced to change. We can have some movement towards the right answer. So the first question that we can ask ourselves is, what instructions actually deal with memory? Okay. So what are these instructions?
Load store.
Load word, store word. What type are load word, store word?
I type.
I type. Now what happens in load word, store word?
Take the memory address and you either put the data in there or get the data from it.
Yeah, so how do we get the memory address? Someone else. What are the two components to a memory address? If either on load word, store word, it's the same process.
The register and the offset.
It's register offset. What do I need to do with them?
And
So what's going to do that?
the
ALE. So what comes first?
daily.
ALE. So the ALU will always perform an operation before accessing data memory because we need to calculate the real address, which is the register is the base address, immediate is the offset, right? Even if the immediate is 0, I still need to do that add, right? So this one is A. So the ALU always performs an operation before accessing the data. So now we know register file comes first, then the ALU, and then memory, right? So that's the basic ordering of these three components so far, right? This is our conclusion. Draw the register file before the ALU, and the ALU is before memory, okay? So here is going to be our simplified view of this. Excellent. So we have PC. This is instruction memory, right? So of course, instruction memory, we need to access that first. And this is kind of abstracted because usually instruction memory, data memory, they're the same thing. But you also are usually having a separate instruction cache than data cache. So we'll talk about that in chapter 7 with caching, but this makes the view a little bit more simplified and easier to understand that they're these separate entities. So we have the program counter pointing towards the address of the instruction that we want to perform. And out of the instruction memory, we get the 32 bits instruction, right? And then from the instruction, we can get what is RS, right? It's always in the same spot on the instruction. What is RT? Always in the same spot on the instruction. And then if we need it, based on, do we see that the opcode says it's I type? Or is it R type? It's R type. This is the destination. This would be RD. If it's I type, the destination is RT. Okay. So we would need some sort of way to select whether this inputs into the register file would be RD or RT. So if we're selecting the component that we would add, combinational digital logic components. We've talked about it before. It's in ALUs. Mux. Yes, a multiplexer. Mux. Mux is what we use to select things. So that would go here, but again, this is the simplified view. So we're just really showing the ordering here. But then once we have those registers, right, then we can get the data out of them. And this would be always RS to the first input of the ALU. And then we have RT as the second input. Or we have coming from the instruction. It's not an address, but it's the immediate. It's a part of the address, right? So again, I need to be able to select between two things here. So same components, I need a mux here to select. And then sometimes RT is going to be the data that we're storing into memory. Okay? So that's why we have this connection here. And then the ALU is going to be that memory base address plus immediate into the address, or it's going to be the result of the R type add, subtract, things like that, and be sent back over here. But the other thing that can be sent back over to the register file is from a load word. So again, here I need to be able to select, am I getting the data from the ALU or R type, or is it coming from a load word? Okay. So again, this needs another multiplex. So multiplexers are going to be all over this data path. Okay. And we also need to update PC. So PC would need to be having a little adder over here, right? PC plus 4. And then a little bit more for when we add branching to this data path. Okay. So we have these basic logic blocks. There are two different kinds. There's combinational logic blocks. So these are logic blocks with no memory. The output is simply a function of the inputs, and the same output is given for the same inputs. So combinational blocks in here. We have the ALU, multiplexers, things like that. And control would also be a combinational block. And we also have these sequential state elements. So logic elements that contain a state, memory, store information, and the output is going to depend on the inputs and also the value stored in. So register file. The data I get on the output of the register file depends on what is the address, which is the inputs, and what is stored in that register at that address, right? So that's what it means by the input. The output depends on both the inputs and what's stored, right? Because I can give the same inputs, but if the register changed, then my output would be different. So here are our basic combinational elements that we need. We have AND gates, we have an adder, the ALU that we made, in the previous lectures, and the multiplexer that we haven't added to the data path yet, but they will be added. So our sequential elements, like the register, is going to store data in the circuits. And it uses this clock signal to determine when to update the stored value. So this is mostly review, right? From 231. So we just want to make sure that we understand that we are using these edge triggered flip-flops, right? So this edge defines when the signal can be read and when they will be written. And we update when the clock changes from 0 to 1, usually. Usually it's always rising edge. That's the convention. So rising edge is here, right? Clock goes 0 to 1. So that means that the inputs into the flip-flop, which is D, can now be stored into it for the next clock cycle. And the output Q would update to what D was. Okay. And then falling edge also works. But again, the convention is like this diagram where we're updating based on rising edge. So we have these setup and hold times, right? So your signal that you want to change the flip-flop to needs to be steady sometime before the rising edge and also after the rising edge in order to properly capture it in the flip-flop and output it. And then during the whole clock cycle time, then the inputs can be changing. But again, it has to be stable. So this is where it's changing, right? But it's stable before the rising edge. And again, over here, it's stable before the rising edge and also stable after. Right? There's some time after the rising edge that D is still not changing. We have the D flip-flop, right? It's the single input D, and the output Q follows D at the rising clock edge, and it stays for that single clock cycle, right? For the whole clock cycle, it will stay as what was input at D. Again, this is just the same waveform that we were seeing before, except now we're directly looking at one single bit rather than this can be anything. We're just saying that it's stable here, changes here, stable here. And again, where our clock transition is at pause edge. So D at pause edge, D is 1. So Q will change to 1 for the whole clock cycle. This was the beginning of the clock cycle, end of the clock cycle. And it does take some time for D to pass through to Q, which is what this delay is, right? And then again, next pause edge, D is still 1, so Q just stays 1. At this pause edge, D is 0, so Q changes to 0. Pause edge, D is 0, Q changes to 0. Pause edge, D is 1, Q changes to 1. The next poll that you have is which is true about the register file? Oh, it's just stretching. This one, I think, was relatively quick. Is anyone still thinking about this? So we are very close to the threshold, so we can just go over this together. So what is true about the register file? And it's just asking about writing to the register file, right? So do all instructions write to the register file? So what are some examples of instructions that do not write to the register file?
Jump.
Mhm.
Right.
Yep. What else? There's also store word. Store word writes to memory, not the register file. So there are all of these different types of instructions that do not write to the register file. So A is not true. What about some instructions write to the register file? We better have some instructions write to the register file, otherwise what's the point of the register file, right? So these instructions are R types, load word, some I types. Okay, and then C, definitely not true. If no instructions wrote to the register file, we wouldn't have one, right? And then D, the register file is a combinational. We talked about this, right? The register file is a sequential because it has this stored memory, the 32-bit register. Okay? And each of those 32-bit registers are just an array of D flip-flops. So not all instructions require writing to registers. That means that we should have this write control signal. So we're basically going to enable writing to the register or not. Because if an instruction is not meant to write to the register, then we for sure don't want it to happen, right? So this is our register with a write control. So in this case, we're only going to update on the clock edge if write is 1. And if write is 0, we just keep the stored value. So here we can see that. So pause edge, write is 1. So we're enabled. That means that we're going to write D into the register file and save it as Q for 1 clock cycle. But on this pause edge, write is 0. So we're not going to update Q based on D. So even though D changed here, right? We are staying. I mean, it changed here. And it would be an updated value of D here. Q stays the same. Q doesn't change. Okay. Then on the next one, write is 1. So this update is written. So similar to the register file, memory is also going to have this write control. So with this edge triggered methodology, our inputs to a combinational unit are values that are written in a previous clock cycle, while the outputs are values that can be used in the following clock cycle. So we get this register updated at pause edge, and while this one is updated, well, before this one is updated, during that same clock cycle, the output of this one is going through the combinational logic and going to update this register. Okay. So these two registers will be updated at the same time. The key is that we have to have this cycle time long enough where the outputs from this one can flow through the combinational logic and get captured properly by this register. And this cycle time needs to be accommodating for every single one of these register to register paths. So even if we have a path that takes 2/3 of the time of the longest path, it's still going to take the same amount of time as the longest path, because our clock cycle is determined by the longest path. And this is our typical execution. So read the contents of the state elements, send those values through the combinational logic to compute the new ones, write the results to the register. And at the same time that the results of this combinational logic is being written to this register, the combinational logic over here result is being written to this register. Right? And like we talked about, longest delay determines clock period. And one thing that we keep in mind is that we have this window around the clock. And the clocking event is the pause edge in most cases, during which the input must remain stable. So we have the setup time, right? Which is before the clock edge, and the hold time, which is after the clock edge. So we not only need to have the time to flow from this register through the combinational logic to this register, but on top of that, we need to have this setup time. Right? So that gets added to our minimum clock period or maximum frequency. They're the same thing, right? And the other thing that we have to worry about is at the clock edge, this flip-flop is potentially changing, right? And if this change flows through the combinational logic too fast, and our inputs into this flip-flop is not stable for the whole time, then we could not capture the data properly. So we have to also make sure that the delay between this flip-flop and this flip-flop is long enough to ensure that the data is stable for this whole time. Okay. So this is our definition of these things. Setup time, minimum time before the clocking event by which the input must be stable. And hold time is minimum time after the clocking event until which the input must remain stable. Okay. So again, this was a review, right? But it is critical to understanding our data path. Not for the single cycle just yet, but for pipeline in the future. It's much more important. All right. So for Monday, we have reading for the next part of the chapter, and we're going to continue single cycle. But since we do have some time, I do want to talk to you guys about the group research project that you do have. You will be working in groups, and you'll work on signing up for one of the 10 papers. And the 10 papers are kind of incremental improvements on CPU architecture, mostly from the 90s. So because if I gave you papers from now, it would be very hard to understand. But these other improvements from the 90s will be much easier for you to understand and be able to present and teach everyone that improvement. So I will post a spreadsheet with these different papers onto Piazza. And it is, well, that's what I'll do. And I'll also post another spreadsheet for you guys to make your groups. So those will be the two spreadsheets that we'll post initially. There'll be a third one later down to sign up for what day that you prefer to present. But yes.
How many per group?
So usually maximum of 4. Because we don't have 40 students. And there's 10 papers. So maximum of 4. And we'll do it, I'll post this spreadsheet sometime today. Deadline will be next week. If you do not have a group on that spreadsheet by class time Friday, you are going to be randomly assigned a group. And then after that, if you have your group, then you can also put your preference for which paper you want to go over. So the other spreadsheet will be just listing your preferences. And that one won't be due until you have your groups. So it'll still be up, but you need to form your groups first, and then you can fill out the other spreadsheet. The other spreadsheet will be due the following week on Friday. So basically 1 week after groups are finalized, then 1 week later, the paper for your group will be finalized. So is there any question on that? The presentation will be 10 to 12 minutes. So maximum is 12 minutes, minimum is 10 minutes. And then it should be 3 minutes of questions. And the expectation is that you will ask questions if it's not your presentation. It's not going to be that I have to ask all the questions. Okay? And your presentation will be on the very last week, so week 15, plus the Friday of week 14. As we just need those 4 lectures to get through 10 groups. All right, so is there any other question on that? We'll ask them later on when it's closer to where you're actually working on. 2 spreadsheets. If you don't see them, you need me. Make sure that I get them posted onto Piazza.